This is the last module for the course SEMU2113. The module is on energy analysis of open systems. It will cover mass and energy balance for a control volume, steady state, steady flow process for a control volume, and finally the energy analysis on some steady flow engineering devices. Let's have a look at the mass balance for a control volume first. According to the Einstein equation, energy and mass are interchangeable, but the amount of mass is too small in our analysis, in thermodynamic analysis. So for this course, we are just concerned with the conservation of mass, mass into mass, and energy into energy. For closed system, previously, mass is conserved. That is called control mass or closed system. In an open system or control volume, mass can enter and leave and carries with it energy, flowing through pipes and ducts. And for a compressible flow, where the density is considered uniform over the cross-section area of the channel, we may describe the mass flow rate with 5.5. Now, the V is V average, which we will drop from here onwards, because actually in channel flow, the velocity varies along the radius of the channel, especially close to the entrance region. So we assume that V is average over the channel cross-section, pipe ducts. Sometimes the volume flow rate is given instead of the mass flow rate. Mass flow rate is in kilogram per second. When volumetric flow rate is given, it's in meter cube per second. But you may get the mass flow rate from that by dividing it with the multiplying the volumetric flow rate with the density. Now, the conservation of mass in a control volume may be stated by 517. That means you consider mass flow rate in entering the control volume through all the available inlets minus total mass flow rate leaving the control volume. There may be more than one exit, which is equal to the rate of change of mass in the control volume. It's given in this equation. For steady flow processes, the amount of mass in the control volume is constant. So you have the rate of change of the mass in the control volume being 0, and the equation 517 is simplified into this form. For many engineering devices, we have only single streams. That means one entrance and one exit. So 518 is simplified into 519. So you just have the mass flow rate coming in is equal to the mass flow rate going out. This is for steady flow processes for single streams, one inlet and one exit. Now for an incompressible flow of a working fluid such as liquid, so the density is not changing. The equation 518 is simplified as this, and for single stream, it becomes just the velocity multiplied by the cross-sectional area at the inlet equal to the velocity multiplied by the cross-sectional at the outlet, 521, assuming the cross-sectional area at the inlet and outlet is different. The velocity is of course different. Now if these are all the same, you get very much a simplified version of the equation. Flow work and energy of a flowing fluid. Now, unlike the control mass, now we have a mass coming in and out of the control volume. Now, the element of a mass carries with it energy as it enters and carries with it energy out as it leaves the control volume. So, the workflow is just the force pushing the fluid element in or out multiplied by the distance it moves. So that's 523, which is simplified with just pressure multiplied by the specific volume. 524. Now, if this flow work is expressed in terms of properties. Pressure is a property, intensive property of the system, so is specific volume. Now, if you include that in your conservation of energy equation, so the total energy of the simple compressible open system, considering the flow energy, is now become this. So here the energy is now equal to the flow energy plus the internal energy and the kinetic energy and the potential energy in kilojoule. Now, if you use the definition of enthalpy, you may simplify the terms PV plus U into H. So you get this energy to be equal to 527. Note again the units is in kilojoule per kilogram. Okay. Many engineering devices such as turbines, compressors and nozzles operate under steady state, steady flow conditions once the transient startup period is completed. So, during a steady state, steady flow process, what does that mean? There is no change in properties within the control volume. Yeah? The mass entering is equal to the mass leaving. The working fluid properties at the inlet and exit are constant, although they may be different. Yes. It is further assumed that the flow properties are uniform over the cross-section of the inlet or exit section, and the heat and work interactions between a steady flow system and its surrounding do not change with time. Yeah? And we simplify the mass balance for a control volume undergoing a steady state, steady flow process with 531. Again, if you have more than one inlet, then you have to sum up. Say, maybe you would like to label the first inlet as 1A, the second inlet as 1B, and 1C, and so on. So you sum them up, which is equal to the exit. You know, you may label the first exit 2A, second exit 2B, and so on. In the ebook, they call it by 1, 2, 3, 4, and so on. It's up to you as long as you keep track of what means which. Okay. So, for a single inlet label 1 and a single exit label 2, you get 532. You know? That is mass balance. Okay, let's have a look at the energy balance for a control volume undergoing a steady state, steady flow process. So you have this equation, yes, but the rate of change of energy in the control volume is now 0, and simplifying you get 537. Now again, the summation goes over each inlet and each exit. Yeah. So this term here, yes, that means if you have, let's say, the simplest two inlets, yeah, you have the mass flow rate at the exit, the first exit, multiplied by the properties at that exit. Yeah. Add to that of the mass flow rate at second exit and the properties at the second exit, minus, and similarly done for this term at the inlet. Yeah. Now, equation 537 has assumed that the net heat is into, yeah, because it's a positive quantity, yeah, into the control volume, and the net work is done by the control volume, negative, done by the control volume. So, for the final outcome with the negative Q or positive W, the direction of each must be reversed. So, check out what does this mean. Yeah. For a single inlet label 1 and a single exit label 2, we have here this equation, right? So, single inlet, single outlet. So, mass flow rate is the same. So, conservation mass is the same. Mass coming in equal to mass going out. You take them out, take it out from the, this, factor it out, you get 538. Per unit mass basis, you get 539. When there is negligible changes in kinetic energy and potential energy, most often the case, now the energy balance reduces to just this. Now, if you look at 538, yeah, this form, this is 538, must understand what does that mean. That Q dot is the net rate of heat transfer between the control volume and its surrounding. Yeah, so all heat interactions must be accounted for. This is net. Yeah, and it's negative when the CV is losing heat. Right now we are considering it positive. Yeah, it is 0. Q is 0 for an insulated adiabatic system. We assume it's perfectly insulated unless otherwise stated. Like for instance, some percentage of the heat is lost or gained. Okay. Now the W, the work, is under steady operation. So shaft work and electrical work are the only forms of work involved for a simple compressible system. It is 0 when no shaft or electrical work is involved. The change in the enthalpy between the exit and inlet may be determined from the property tables for liquid vapor states. Yeah. If you use the two property rule or the previously presented to you. In order to get enthalpy at the exit, you need two independent intensive property. You may be given the pressure, specific volume, and the temperature. Then you can get the enthalpy at that instant, the state of the working fluid. Same goes with the inlet. Yeah? So to get this, you need first two independent intensive properties. Yeah? For ideal gases, this difference of exit and inlet, for single exit, single inlet, it may be approximated by just Cp average T2 minus T1. This was presented in the preceding module before this. Yeah? And then the change of kinetic energy, remember, because the unit is in joule per kilogram overall, after you have completed this, the term must be multiplied by 10 to the power minus 3 to have the terms in the energy balance homogeneous. Yeah? So check out carefully the units. Right. Yeah. For the change in potential energy, it is a small quantity and is generally ignored unless the elevation distance between the inlet and exit is large, and it's only significant when it involves pumping work. These two equations are important in the energy analysis of open systems, control volume, under steady state, steady flow conditions. It's a basic equation. Yeah? Condition is conservation mass and energy for steady state, steady flow conditions. Very general. It covers multiple inlets and multiple exits. For single inlet entrance and single exit, you have these two equations, right? Whenever you perform thermodynamic analysis on an open system for under steady state, steady flow conditions, you may have this for single inlet, single exit. For the next part, we shall look at the various some engineering devices to perform our thermodynamic analysis, and we will utilize heavily this conservation of mass and conservation of energy described just now.